In the last lesson, we looked at proportions, and now we're going to look at averages or means, and you'll learn that the ends justify the means. So we're going to look at what happens with distributions, and you can find a stacklet like this, or an applet, I should say. It's the same one I used on the very first lesson for the unit. And you can actually draw the different sampling distributions are specified as normal. And it will show you what the distribution of statistics looks like for different sample sizes. Here we have sample size 2, then sample size 10, and sample size 25. Okay, let me go ahead and just kind of get this so it's easier to point. Now, you can see that these are all centered under the same as the parent distribution. So the center doesn't change because that's determined by the population parameter, all right? And if we compare the shapes for the different sizes of n, all three look normal, like the original population distribution. If we compare the variability for the different sample sizes of n, the same, your spread is decreasing pretty much in the same way that it does for sample proportions. In other words, by the square root of the samples. But what if I look at a different distribution, say a uniform distribution? Would I expect the means to be normally distributed then? So what I'm doing is I'm drawing samples. Here's sample size 5. And I keep adding to it. And then I'll eventually here get quite a few more samples. So you can see there's 5 and there's the mean. Another 5 and there's the mean. And then another 5 and take the mean. So that creates a blue dot. Well, we can keep doing this, or we can actually speed it up here in just a sec and get a bunch more samples. And here's 10,000 and 100,000. So once you start taking a lot of samples, you see that the shape is actually, whoops, sorry, didn't mean to do that, is actually pretty normally distributed. What if I'm taking with a samples the size 25? So it takes a little while because I'm collecting 25 data points, then averaging them, and that gives me a blue dot. What you're probably going to notice is that the spread's going to be a lot smaller because it's a lot harder to get a mean, have all your samples be on this end of the curve and have a mean that's smaller. So your spread's going to decrease with the square root of n. Okay? So even for a uniform distribution, the means are approximately normally distributed. The variance still decreases with increasing sample size. So if I fill in your sketches and your notes, that's what I would draw right there for this roughly normal distribution. But what if I gave you a really crazy distribution where it's pretty extreme? I could easily have means over here and here. So let's go ahead and take a look at what that looks like. So first of all, I'm just going to do sample sizes of 2. And it's not impossible to get 2 on the high end, or 2 on the low end, or 2 in the 1 on each end, or maybe even 1 in the middle. But you can see I tend to get one or the other. I get 2 here, 2 here, or 2 here. And this leads to this crazy distribution. Oops. All right. What if I go with a larger sample size? Here I'm using a sample size of 5. And it's still pretty crazy because I can still get really extreme values. But what if I go to larger samples, the sample size 25? All right. I'm sorry, these are sample size 10. So now it's starting to look a little more like what you've seen before. It's kind of normal. Now we're doing sample sizes of 25. See how I gathered 25 data points, added them up, and then put the average here. And when you take a lot of samples there, you can see it actually looks very much like the normal. So you would go ahead and fill in these sketches on your notes. And you can see for what values of n were we able to get an approximately normal sampling distribution for every distribution, whether it was really crazy like this or this. Well, once we got up to about 25, we had a very nice value. But in reality, we're going to use a slightly more conservative value of 30 but we were able to demonstrate it with 25. All right, so when sampling distributions were large enough, we could say that they are approximately normal, okay? Then we can use our knowledge of combining random variables. We can calculate the average and standard deviation for a sampling distribution. So what is the average of the means? Well, it's just going to be all the means added up by how many I take, or pretty much just the mean for the population. So what about the standard deviation? Well, I'm going to go ahead and add the variance. Now remember that we are actually dividing by n because we're dealing with averages. So I'm going to take each standard deviation and divide by n for each of my variables. Remember, you can division on a standard deviation, that applies. So I'm going to end up dividing them by n, but I have to square them and add them up, right? And to get the standard deviation, I take the square root of the variance. And I can go ahead and get a common denominator here because I'm going to get sigma squared from that one plus that sigma squared, and I have an n squared here. If all the standard deviations are roughly the same, which we're assuming, then I can just say, hey, there are n of these sigma squareds on top, and then that simplifies to sigma squared over n. Well, the square root of sigma squared is just sigma, and just write that as square root of n. So the standard deviation for sample means, like we saw before, goes down by the square root of n. So the larger the sample size we have, the less spread we have. So the central limit theorem is when n is sufficiently large, that is, in our case, n is greater than or equal to 30, the theorem tells us that the distribution for means is approximately normal, even if the distribution of the population is skewed. So if we have a big enough sample, we don't care what the population looks like. The x-bar for the sampling distribution, or the average, is the same as the mean for the population. The standard error or deviation, depending how we work with this, that's a hint of the future, of the mean distribution is about square root of n times smaller than the population standard deviation. And the reason is it's harder to get on the extremes when you're averaging from your sample. Probabilities for sample means are calculated in the same way, except you have a smaller standard deviation for the mean of the sample. Now, as we mentioned before, conditions are critical to make sure that we are using the right model, that we didn't break it. So first of all, we want to know about the shape. And we use the normal large sample condition, all right? Not large counts, just large enough sample. So there are two ways to make sure your shape is good. If your population is already approximately normal, if you remember that first slide, even when n was 2, it still looks normally distributed. So if the parent is normal, then the samples coming from it will be approximately normal, all right? Now, even if you don't know what the population is, if they don't tell you that it's normally distributed, if it's at least 30, then we're fine. We can invoke the Central Limit Theorem, or CLT, which basically tells us that over many, many samples, it's going to start to approach the mean. So basically, there's no strong skew and no outliers, all right? Now, we need independence also for our standard deviation to make sure the probabilities are the same for each trial. So this is usually called the random condition because independence is going to usually be obtained through good randomization, all right? Now, if we are going to combine variables, we need to make sure that our estimate of standard deviation is useful, and that's met by the 10% condition. Sometimes you're going to have to say it's reasonable to assume one of these conditions if it is actually reasonable. So in 2017, we're going to look at SAT scores. The mean math SAT score was 527 with a standard deviation of 107. Since the SAT is standardized and the graph at right is fairly symmetric and mound-shaped, it is reasonable to assume that the population of SAT scores is approximately normal. All right, so we're going to draw the model. There's our mean and our standard deviation, so I can just basically fill that in. So what's the probability that an individual student scores over 600 on the SAT? All right, so we've told you you can use a normal distribution. We're curious about over 600, right? So our random variable is X, which is one individual SAT score. We're just picking one. It's not a sample. Well, sample one, I guess. And our model is for that one individual is that it's approximately normally distributed with a mean of 527 and a standard deviation of 107. So then we write our probability statement. We want to know the probability that X is greater than 600. So we basically go to the calculator. So we're going to go down to distributions, and it's normal. Our mean is 527. Standard deviation is 107 because we're talking about the individuals. And we want the probability that it's greater than. So I want it pointing greater than or equal to 600. You're probably going, oh, but what if it says greater than versus greater than or equal to? Remember that for these distributions, it's continuous, so it's not a big deal. All right, and so we get 0.2475. So we see that our final score was 0.2475. Now, if we take a random sample of 20 students and record their scores, can we use a normal distribution even though n is less than 30? So remember, this is helping to define our shape. So yes, because the population is approximately normal, it doesn't matter how small a size. Remember on the first page of notes for this lesson, even when the sample size was 2, it was still approximately normal. What would the center be for sample size 20? It should be the same. What would the standard deviation be? Well, we just have to divide by square root of 20. So we would get 23.9. Now, what are the mean scores for the middle 95% of samples? Well, we can just basically, we have our model. So it's a little different than what we had before. You can see it's tighter now. And so if we use the empirical rule, we just say 2 standard deviations away. So basically 479.2 to 574.8. So what is the probability the average score for our sample is over 600? Well, we are going to define our random variable. So now we're talking about a statistic, which is the average SAT score for n equals 20. And so it should have a mean of 527. It should be normally distributed, and we have our standard deviation that we just calculated. But we're going to double check conditions to make sure we didn't break this. Our center is okay because it is a random sample. I know you don't see it on this screen, but earlier we told you we were taking a random sample. The shape is okay because the original population is approximately normal. So if the parent's normal, we can say that the sample statistic should be approximately normally distributed, all right, even though we're only taking a sample size 20. The SD, or standard deviation, is okay because 20 is definitely less than 10% of all SAT scores. So we write our probability statement, and we're saying the probability that our sample statistic is greater than 600 equals. And so we just basically go to the calculator with our model. Now we're going to go backwards, hit that little back button, and the mean stays the same, but the spread changes. So it's now 23.9. And we still want score being greater than 600, so make sure and change that. 600. And now you can see the probability is much smaller. It's 0.0011. So you can see we got an answer of 0.0011. So if we want to interpret this, we would say in repeated samples of, and then we got to do sample size and context, about some percent of the samples would. All right. So in many, many repeated samples of 20 SAT scores, about 0.11 would have an average score over 600. In this example, we're looking at mean birth weights. At birth, babies average 7.8 pounds with a standard deviation of 2.1 pounds.
A random sample of 34 babies born to mothers living near a large factory that may be polluting the air and water shows a mean birth weight of only 7.2 pounds. Is that unusually low? So we'll need to calculate a probability, and we will need a distribution. And of course, we need our random variable, which is our sample statistic, the average weight for a sample size of 34. So here's our mean at 7.8 pounds. Let's go ahead. We know the population standard deviation is 2.1. So we're going to calculate the standard deviation for the sampling statistic. And we do that by just taking the population and dividing by the square root of the sample size, 34. And we get 0.360. So that gives us a model for the sampling distribution that it's normally distributed or approximately normally distributed with a mean of 7.8 and a standard deviation of 0.360. But before we do any calculations, let's make sure we didn't break it. So let's start with the center. Center is okay because they told us it is a random sample. All right, so we're fine. Then we need to check the shape. Well, we took 34 samples. So even if the original population was not normally distributed, because it doesn't say anything about the original population, our shape's okay because our sample is large enough. Then finally, our spread, well, we have to make sure we didn't sample more than 10% of all babies. We sampled 34. So an easy way to do that is to take that sample size and multiply it by 10. Is it reasonable to assume that there are at least 340 babies born to moms living near the factory? And it is. So then we do our probability statement. We're interested in low, and our sample was at 7.2. So we want the probability of getting a sample statistic of 7.2 pounds or lower. So now we take our model and go to the calculator. Now we're going to make sure we set this up for the babies, and our average is 7.8. Our standard deviation is 0.360. Next, and our probability statement says less than 7.2 pounds. Again, don't worry about the equals on this because it's continuous. And our answer is 0.04779. Just double checking all my values. 7.8, 0.36, 7.2. All right. So our value is 0.04779. In repeated random samples of 34 babies born to mothers living near the factory, about 4.78% would have an average weight of 7.2 pounds or less. For us, this is unusually low. You could argue, well, you're almost 5%, but it is below 5%, and that's pretty much our guiding principle. It's lower than 5% probability, so this is unusual.
So sampling distributions for the difference of two means. Sometimes you want to compare quantitative values for two populations. A lot of times we want to do that. So we're going to go ahead and use what we studied with random variables and how we could combine them if they were approximately normally distributed. So if both samples meet the 10% condition and the large counts condition, we can use the following rules to combine them. Remember, when I'm doing means, it behaves like the equation. Mean of x1 plus or minus mean of x2 plus or minus, etc. Mean of x to the n. And that should really have a minus sign. Variances add. They do not minus. And so I would add the variance for each one. But remember that variance is standard deviation squared. So I would take the square root of the sum of the standard deviation squared. Again, remember, variances always add. So if I was just looking at the difference of two means, let's get a little more specific. I would basically say, oh, it's just going to be mean for 1 and minus mean for 2, and it's straightforward. The variances, because I can have this formula, there it is for sample 1 and for sample 2, and when you square them, you get that. And then to get the standard deviation, we're just going to square root this, and there's your formula. The standard deviation of the differences is the standard deviation for your first population squared divided by the sample size, plus standard deviation for the second population squared divided by the sample size, take the square root. So what about conditions when looking at differences? We have to meet the same conditions for each individual sample. So we have the random condition that the data come from 2 independent samples or from 2 groups in a randomized experiment. We still have the 10% condition when sampling without replacement, which is almost always. Then we need the N1, sample 1 is less than 10% of population 1, and sample 2 is less than 10% of population 2, if there is no replacement. Sometimes you can actually have trials and experiments where you can keep trying and there's no real limit on the population. So we also have the normal large sample condition for each sample group. The parent population is either approximately normal, in which case you're done. You're like, oh, if the parent's normal, then the averages are normal. Or the sample size is large enough that it's at least 30 so that the averages are normal, even if the parent is not normally distributed. If it's less than 30, and we're not sure if the parent population is normally distributed, we can actually graph the sample data. And as long as there is no strong skew or no outliers, both have to be satisfied. Then we can say, okay, we're fine.
Now we'll look at AP Stats and the SAT. So in 2017 and 18, 605 and 613 Round Rock ISD students respectively took the AP Stats exam, and average scores increased from 3.50 to 3.56, even though worldwide the average did not change. The average SAT score for worldwide also remained the same from 2017 to 2018. So they took 2 random samples of 50 Round Rock ISD SAT scores, all right, one from 2017 and one from 2018. The sample means were 1104 and 1125 for 2017 and 2018, respectively. Assume the population's standard deviations were 215 and 211. Now, assuming the true mean Round Rock ISD SAT score also didn't really change from 2017 to 2018, let's calculate the probability we would see a difference this big in sample means when taking random samples of size 50 from each year. So this is our sample statistic. X bar is 2018 minus X bar for 2017 is 21. I got that by subtracting 1125 minus 1104. Now, our random variable, if we were to take many of these samples, because we're trying to model a sampling distribution, then the average, we would represent that by X bar of 2018 minus X bar of 2017, all right? And our mean, true mean, we told you that assuming the true mean didn't change, then they would be 2 of the same values. When we subtract it, we get 0. We have the population standard deviations here, so we can actually calculate the standard deviation for our sampling distribution. We just have to square the standard deviations and divide by sample size, add them, and then take the square root. We get 42.6. So now we've got a model for these sampling statistics, for the difference of means, right? And it's normally distributed with a mean of 0 and a standard deviation of 42.6. Now, we're going to double check that this distribution, that this model isn't broken. Well, we gave you that we took random samples for both years, so our center is okay. Then we want to check our shape, and that has to do with how many samples we got. Is this normally distributed? Well, I didn't say the population was, so we have to look at sample size. Well, both of our samples are 50, which is definitely more than 30. So we're fine, it's sufficiently large. Finally, I need to check that standard deviation. And to make sure that my sample isn't going so big that I'm taking up too much of the population. So SD is okay, our standard deviation is okay, because 50 is less than 10% of all Round Rock ISD scores for both years. So our conditions are met, and we can go ahead and create our probability statement. We want to find the probability of a difference at least as big as 21. So now we go to the calculator. Even though it's a mean of differences, we already have our mean difference. We're saying it's 0. So let me get rid of this 7.8 from the babies. And our standard deviation is 42.6. And we want to know the probability that we would get a difference as big as 21 points. So I need larger than 21. And I get 0.31102. Or basically 0.3110. So we got 0.3110. Let's interpret that, okay? In repeated random samples of 50 SAT scores from each year, we expect the samples to have a difference in mean scores for those 2 years of at least 21 points or higher, 31.1% of the time, assuming the true difference is really 0, all right? If I want to interpret the mean, over many, many samples, we expect the difference in scores for 2017 and 2018 to approach 0 points. And the standard deviation means the difference in points gained, 2018 minus 2018, for the mean scores typically varies about 42.6 points around the true mean of 0 points.